acyclical finite state devices are a dream come true for modular synthesizer people who want random melodies and random ambient noodling where they can just sit down and wait for something to happen hour after hour. And today we are going to build a simple acyclical finite state machine and demonstrate the behavior of the animal. Now, one thing I would like to tell you is I'm going to do a theory video to show you how to design them. And in a minute you're going to see the circuit diagram and the state diagram. But consider as you watch the video what would happen if you drive the X and Y input from a random voltage source. And also consider the fact that not only can we increase the number of states, but we can also increase the number of inputs. Even this simple 2-input 4-state model I could show you is capable of a lot when put into a modular synthesizer, and perhaps we'll do that in another video. But the whole real purpose of this today is for my students at the university who are building the circuit now. So the theory and the application to modulars will have to wait a while. But as you watch the video, you might be inspired to realize the possibilities, because the output Z, I can put any logic function on that, or even switchable logic functions, to combine the various states of the flip-flops in numerous mathematical ways. So this actually is the basis for a very simple and inexpensive random machine, similar to the Turing machine that these people are using. First we wire the power to the 4 ICs. Starting from the left, we have the 7408, which is a quad 2-input AND gate. Next we have the 7432, which is a quad 2-input OR gate. Then we have the 7473, which is a dual JK flip-flop. And last on the right we have the 7404, which is the hex inverter. Notice that the JK flip-flop has the power reversed. The plus 5 volts is from pin 4. As you can see, that's the only one with the red on that side, and the ground connection is on the other side from pin 11. This is why we have to use both plus and negative rails on both sides of the IC, because some of the ICs reverse the power connection. In stage 2, the clock has been connected. The two clocks have been connected together and connected to the pulsar button. So blue has been used for the clocks. Yellow has been used to connect the inverters between the J and the K for flip-flop A and flip-flop B. And the two clears have been connected to the power, so red have been used to connect that. So we have two red ones for the clears, two blue ones for the clocks, and the J and K connected through the inverter below. It comes up in 1, state 1. So let's see what happens in state 1 when we have 0, 0 and we pulse it. When we have 0, 0 and we pulse it, we get an output in state 1. When we switch to 0, 1 here, and we pulse it, we get a 1, and it transitions to 3. And when we go back to 0, 0, and we pulse it, we get a 1, and it transitions back to 1. So we've proved that loop. So the only other thing we need to do now is to go 1, 0, and we should not get an output, and it should transition to 0, and it does. Once we're in 0, we can go 0, 0, nothing happens, no output. We can go 1, 0, and we pulse it, nothing happens. We can go 1, 1, and we pulse it, nothing happens. But when we go 0, 1, and we pulse it, we get a 1 output, and it transitions to state 2. Perfect. So that's checked all the options of state 0. Now in state 2, when we have 0, 1, it will output a 1, it will output a pulse but not change from 2. And when we go 0, 0, there will be no pulse output, and it will go back to 0. So let us go back from the 0 to the 2. Pulse, go to the 2, so that we continue to explore the 2. Now when we have 1, 1, we will move from the 2 to the 3 with no output, and that happens. When we are in the 3, we can have 0, 1, and we get a pulse output. 1, 0, and we get no pulse output and no change. 1, 1, no pulse output and no change. But when we drop to 0, 0, we get a pulse output and go to 1. So we've tested virtually all except for the dual changes. So when we come down now to the 0, we come on 1, 1. No output there. We can take 0, 1 and go to the 2. And we can take 1, 1 and go back to the 3. And we'll have to go around it again in order to take the other route. 1, 0, 0, 1, one, 0, and we've come to the 3. So that's it. Thanks for watching.